Hiya, in this video I'm going to talk to you about scatter graphs, okay? Scatter graphs are great because you can understand them at a very basic level, but then they go up to A level and beyond, and there's a lot more complicated techniques we can use to improve our understanding between what's called bivariate data, okay? So I'm going to introduce this at a very basic level first, because you might be a Year 7 student tuning in or a GCSE student, but then I'll progress it up to an A level standard, okay, for statistics. So first of all, it's about bivariate data, okay? So that's a key term you need to know, bivariate data. That is when you've got paired data variables, okay? You've got two different variables and you've got data that are paired together. When you don't have bivariate data, you might just have one set of data for one particular variable, and then you might use, for example, a cumulative frequency graph or a simple bar chart or pie chart or something like that, okay? But when you've got two pairs of data, then commonly we put the data into what's called a scatter diagram or a scatter graph. I prefer a graph because that's essentially what it is, okay? And the example I'm giving you is for temperature and ice cream sales, okay? Traditionally what you might have is you might have a table of values indicating how many ice creams were sold on a particular day versus what the temperature was on a particular day. And by the way, for temperature you should put in your own units, whether it's degrees centigrade or degrees Fahrenheit, okay? Or Celsius, which is what most people go for in the UK. Okay, and you normally then plot the points. So for example, on a fairly cold day, you might not have many sales of ice cream, but then on the warmest day, for example, you might have quite a few sales of ice cream. And then you put the points onto what's called a scatter diagram. And here represents 10 different points for 10 pairs of data values. And then it's our job as mathematicians or statisticians to try and interpret what is going on, okay? Before we do that, just some more key terms for you. Along what's called the horizontal scale, sometimes called the x-axis, but for example, you wouldn't necessarily label it as x if it's temperature, you'd normally label it as t, okay? But along this horizontal scale, that's where the independent variable goes, okay? Sometimes called the explanatory variable. Along the vertical scale, the vertical axis, sometimes called the y-axis, but I might label this, for example, S for sales. But along the vertical scale is what's called the dependent variable or the response variable, okay? And it's important that you recognise that no matter what graph you're drawing, either in mathematics or in statistics, the independent variable is always on the horizontal scale. So if you're not sure which way to label it, okay, normally you choose which one's the independent variable. Or here's another tip for you. When you do have a table of values, normally it's done in such a way that the one on the top is for the horizontal scale. So for example, put T there for temperature. And on the bottom is normally for the vertical scale. So if you're in any doubt whatsoever, and you're given a table of values, use that one for your horizontal axis, your x-axis if you want, and use that one for your vertical scale, your y-axis if you want, okay? Now, what we then do is we have a look to see what the points on the graph are showing us, okay? And we look to see if there's some sort of relationship going on there. We call this a correlation, okay? And I'm going to write the word correlation there, okay? Now, before I look into the different types of correlation, we need to decide whether it's a causal relationship or a spurious correlation. What's the difference between the two? Well, a causal relationship means that one of these is affecting the other one. I hope you can see from the example I've chosen here that the temperature on a particular day is going to affect the sales of ice creams. So for example, I remember when I was growing up, in the summer we used to like going to the seafront, okay, on a nice warm sunny day, and the ice cream shops will be open and people generally buy an ice cream, okay. Moving to Europe, it's kind of disappointing for me, that thing does not happen, okay. To me, seafronts, sunny day means ice cream, but that's just on a personal level, okay. However, on a winter's day, that wouldn't be our thing, okay. We wouldn't want to go necessarily to the seafront to eat some ice cream because it's cold and you don't want to eat something cold necessarily when it's actually cold in the first place, okay. So I'm hoping you can see that generally the warmer it is, the more people are going to want out and buy ice cream. Well, certainly people like me and lots of people in the UK, I think, okay. That's what's called a causal relationship. One is causing the other, okay. A spurious correlation, that doesn't necessarily happen, okay? It may be that you plot points on a graph and you get something similar to this. However, it might be that the two variables are completely unrelated. That can still happen. You can still have values that are completely unrelated, but draw a graph, it looks like there's a relationship between the two. Let me give you a simple example. Okay, so apparently a study was done on the number of births that took place over a certain month. They record the number of births per day and the number of storks. Those are big white birds, in case you didn't know, with big beaks. Okay, number of storks that were nestled above the places where people had new children come into the family. Okay, and of course the number of storks that are nestled by your house and the number of babies being born should have absolutely no effect on the other. Okay, how can they? Because it's a fairy tale. The fairy tale being that a stork would deliver a baby to its new family. Okay, maybe it happens in cartoons, but in real life it does not happen at all. However, in this particular study, it was found that the more storks that were nestled within a particular area, the more babies were being born. Okay, that's what's called a spurious correlation. Okay, where it looks like there's a relationship on the actual graph, but absolutely no way are the two connected together. Okay, for example, temperature on a particular day and how well particular people perform in a particular test shouldn't really have a particular relationship between each other, particularly if you do the test in the air-conditioned room. Shouldn't really have, but it could be the case that by complete fluke, one appears to affect the other and you get a graph looking like this. Okay, so you just got to be careful. Just because on a graph it looks like there's a relationship between the two variables, there might not be. So just have a think about it before you decide on what type of correlation it is. If there is a causal relationship, then we look to see what type of correlation that we actually have. I'm sure you'd agree with me, this looks like it's a positive correlation. Now I'm just going to take time out for a moment to talk to you about the different types of correlation. Okay, so having decided that it is a causal relationship, we now look further. If it's not causal, if it's spurious, then we don't bother looking into it because it's just a fluke, it shouldn't happen. Okay, so a causal relationship, we look to see what type of correlation we have. Now, for example, these graphs here, it looks like there's a positive correlation. And the reason we can tell is because it looks like there's a general trend with all the points. That is, they're going from bottom left to top right. In other words, as one variable on this axis increases, so does the second variable on this axis. As the independent variable increases, the dependent variable increases as well. Okay? As one goes up, so does the other. As temperature increases, number of ice cream sales go up as well. Generally, when you're growing up, as you get taller, you get heavier. Okay? So these sorts of things kind of make sense. Okay? This is also a positive correlation because the same thing is happening. As one increases, so does the other. But notice, because these points are more spaced out, they're more scattered, okay, hence the term scatter graph, the correlation here is not as strong as here. So we tend to use the words like strong or very strong when the points tend to lie very, very close to a line. Okay, so the closer these points lie to a straight line, a linear straight line of course, then the stronger the correlation. Okay, if they lie on a straight line perfectly, you might call it a perfect correlation. Okay, so you've got strong positive correlation. If the points are even closer, it might be a very strong positive correlation. Here it's still positive because there's a general trend going upwards like that, but it's not as strong. We call it a weak, or you can have a very weak correlation. Okay, let's just have a look at an example where the points are even more scattered. So what I'm going to do is I'm going to have an example of a greater scattering of the points. Does it look like there's any relationship between these two variables? Is it possible to say that these points are generally looking like a linear straight line? The answer to that question should be no. No, the points are almost literally scattered all over the place. Okay, in this particular example, there's no correlation. Okay, we say there's no correlation, no relationship between the two variables. Okay, and the final one is if there's what's called a negative correlation. Do you know what the points look like? Let me just show you as an example of a negative correlation. It might be the case that the points look something like this. Okay, so we draw a few more. Okay, and I've tried to make it so it looks like there's a strong negative correlation there. Okay, that is, the general trend is that the points are going from top left down to bottom right. What's happening is, as this variable is increasing, this variable is decreasing. as one goes up, the other one goes down. Okay, so on my example of ice creams and hot days, it might be the case that if I keep the example of temperature, the sale of coats decreases, for example. Not many people wanted to buy coats when it is the middle of summer. However, when autumn arrives and you've got winter, then maybe have a greater sale of coats. Okay, so as an example, you'd have temperature along this scale, sale of coats along this scale. As the temperature increases, number of coats decreases. Okay, you can see this point here, high temperature, very low sale of coats. Okay, whereas here, a much lower temperature, a much higher sale of coats. So that's an example of a negative correlation. One goes up, the other one goes down. Okay, of course, you can have weaker correlations. All I need to do is just have a greater scattering of the points, and then that would be a weak negative correlation. Okay, so I'm hoping that's clear about what the types of correlation actually are. Okay. Okay, so next I'm going to talk to you about lines of best fit and the regression line. Okay, so having got a particular scatter graph like this, and you've decided that there's a causal relationship and that there's a positive correlation, next thing you want to do is draw a line of best fit. Why? Because it then helps us to be able to make predictions, okay, or to be able to interpret the data a bit more. Now, as a line of best fit drawn by eye, it might look something like that. Okay, what I mean is I've just drawn it roughly by eye. Now the idea is not necessarily just to make sure there's the same number of crosses above the line as below the line. Okay, so for example you can see I've got 3 below and 5 above. That's not what we're looking for. What we are looking for is to try and draw a linear straight line such that the crosses are as close as possible to the line. Okay, that's what we really want. We want to make sure that we draw a line such that the crosses are as close as possible to the line. Now, mathematically, the best way of doing it is like this, by calculating the vertical distances between the line and each cross. Okay, that's what we're looking at. Okay, and what we want to do is have those distances minimized. Okay, we can actually do that using calculus if we need to. Okay, think about it. Calculus is about max and minimum as well. Okay, so we want to keep the distances actually minimized. Okay, however, in doing those calculations, what you'll notice is that the distances we used are going to be a mixture of positive and negative values. Okay, so for example, here these will be positive distances above the line of best fit. These will be negative distances below the line of best fit. Okay, so in our calculations, what we need to do to keep all the values positive is to square the distances. So square each of these distances and then ensure that the mean average of those is kept to a strict minimum. Okay, this is what's called a least squares regression line, not just a line of best fit. A line of best fit drawn by eye, like I did at the beginning, would be enough up to GCSE standard, but to A-level standard and beyond, we want to have a more accurate line. Okay, we want to have what's called a regression line. And traditionally, you work out the equation of it first, and then you draw the line. Okay, because if you think about it, how do you work out the distances with a line that you don't know that's already there? Okay, and I said one way of doing it is to use calculus. In the S1 course, we don't actually need to have to do that whatsoever. Okay. What you can then do is make predictions. Okay, you can make predictions with the data. I'm just going to go off on a slight tangent for the moment, just talk about what you do with the predictions. Now, what I mean by that is, suppose these were results in a test, okay, and this was test 1 and this was test 2, and they're both, for sake of our mathematics tests. Okay, so these are the scores that students got, and generally you can see if they did better in test 1, they did better in test 2, which makes sense. Okay, if you're good in one test, you're normally good in the other test as well. Now suppose you've got a particular student that was present for test 1 but absent for test 2, and there's no way of them taking test 2 whatsoever. Okay, what you might want to do is have some sort of prediction of what the likely outcome would have been. Okay, so suppose you know that along the scale the score for test 1 was there. What you'd then do is you'd read up the scale and then you'd use that line of best fit or regression line to make a prediction. You'd do a read off kind of like you would do with any other graph, like a cumulative frequency graph, they do a read-off, and the prediction would be that if that was the score the student got for test 1, that would be the score that the student is likely to have got for test 2. And that's how you can use a regression line, okay, to be able to make predictions like that. What we've done is we've interpolated with this data, okay? We've interpolated. What that means is, notice that the regression line has been drawn such that it covers the range of data that was initially given, okay? If we want to extend the regression line to cover data outside which was given, that's called extrapolation. And for extrapolation, it's not as accurate, okay? It's not as accurate. It's only accurate enough because we don't know what the trend is necessarily going to be beyond this data point. It will be complete guesswork. So the advice is try and interpolate as much as possible rather than extrapolate, because it goes beyond the data values, okay? I'm going to pause because there's a very noisy vehicle behind me. I'm going to record something else in a minute. Okay, so having got your regression line, what we do is we write it like this: y equals a plus bx. Now, for those of you who remember your geometry, coordinate geometry that is, you've got y equals mx plus c to represent the equation of a straight line. Okay, exactly the same principle. Okay, the a here is the y-intercept, and the b here is the gradient. Okay, so in other words, before you've actually got a line drawn on the graph, if you've worked out the equation of the regression line already, you can tell whether it's a positive or negative correlation by looking at the gradient. Okay, because of course a positive gradient means that the line is sloping upwards like that. If b was negative, it would be a negative gradient. It would be sloping downwards like that. So just seeing what the gradient is, whether it's positive or negative, that tells us whether there's a positive or negative relationship. Okay, this here is often called the y-intercept. Okay, now just remember what I said about interpolation. You should only really interpolate, that is to say, look at data read-offs within the data range given to you. Okay. However, if you were to extrapolate the line both ways, then this would be your y-intercept. Okay. So one simple method of working out what the value of a is to have your line and then just extrapolate. Okay, just draw and see where it crosses the y-axis. Okay. However, in A level, that's less advisable, because really what you're doing is you'll be calculating the equation of the regression line first and then drawing it second. Okay, that's essentially what it represents. Okay, sometimes the data is meaningful, sometimes it's not. Okay, but what the y-intercept traditionally represents is the value of y when x is 0. Okay, the value of y when x is 0. Okay, that's really what it represents. So, for example, in the temperature example I gave you, and sales of ice creams, let's just put in some generic numbers here. Okay, so this being 0, as in 0 degrees Celsius, I'm going to go for. Let's go for degrees Celsius. If this number of sales of ice, let's just suppose I'm going to put it 5. Okay, just for sake of argument, I'm going to label that as 5. Okay, what this would mean is that the y-intercept of 5 would mean that on a particular day where the temperature is 0 degrees, there are 5 sales of ice cream. That's exactly what it means. And all you need to do is interpret it in that way. Okay, in other words, whatever this variable represents, okay, when there are 0 sales or 0 items along the horizontal scale, then there's this many, the y-intercept number of items on the vertical scale. Okay. In terms of gradient, okay, how do you interpret that? Let me just give an example. Okay. Well, I can't tell you what, let's just suppose this was temperature, sorry I'm writing it again, and sales again of ice cream. I can't bother to write it out the second time. Okay. And suppose that the gradient turned out to be, let's just say 2. Okay. Let's suppose that the gradient B, in this case, was 2. What does that mean? Well, it means that for each unit the temperature increases, then the number of sales will go up by this amount. That's what it means. Okay. If this was -2, for a start it would be a line like that. It would mean that for each unit this increases, the number of sales will go down by 2. So that might be the sale of coats example that I was talking to you about. Okay. That's essentially what it means. For each degree, in this case, for each degree Celsius that the temperature increases by, the number of ice cream cells increases by 2. So that's really what the interpretation is all about, okay? That's probably enough up to GCSE standard. I'm going to do another video now, which is going to start basically with this simple information and just go ahead for what you need for statistics at A level, okay? But I'm hoping that you enjoy that and you got something out of it.